perhaps.
All
All right, so you're good to go.
right, thank you.
Yep.
All right, so where does this relate? Okay, so my research in the last couple years has been on the area of ultra low power communication. So the real gist of the development work I've done here is, and with grant money, we've done it at TCNJ, we've done a lot of work in this area. So what I'm looking at is, how do you get to the lowest power platform to communicate? Now, when you think about communicating sensor information or communicating text, it's really the same thing, right? Maybe a different user interface, but it's basically, you can do both. And I'll tell you how I arrived at a lot of that logic. So the first thing I want to do is talk to you about the lowest power communication platform and how it's energy optimized to the point where I can use energy harvesting, which is taking ambient energy and powering the transceiver, which is a neat trick. The other thing I'm trying to do is I'm also trying to go after the greatest or the highest, largest range possible. That's and I started talking about different limits of doing that. There's some limits that Shannon established that I've followed down that path to see how far I can go with lowest power, greatest range, and lowest cost. Now, if you think about when would you really need the lowest power, greatest range, lowest cost? Well, the lowest power is needed when you don't have power, right? Your power grid is down. So my logic in this is how do you get out of a disaster situation, or how do you continue to communicate when there's no power, there is no cellular infrastructure, there's no TCP/IP infrastructure, the internet is down, and do it cheaply, so you don't have to go in often. Cost you $1 million to get to the point where you communicate. Right, right. The scientific field, they call this is ad hoc network, meaning EMP just went off, you don't have power, you don't have anything. There's no cellular communication, there's nothing. But I still want to communicate worldwide. How do you do that? So that's the genesis of this talk. And the funding and stuff and the work I've been doing is in the area of sensors. People, there's a lot of interest in industry about how do you have low power sensors, because if I can deploy a sensor in the field and have it powered by the tree or by the light or by the structure, vibrations in the structure, that's a winning combination. One of my clients is in the construction business, and he has many contracts in New Jersey. When there's another hurricane comes through and they want to rebuild, well, you have to be somewhat intelligent in what you're sensing in structures. So the idea is you want sensors to be able to understand what's going on in ridges, right? Buildings and major structures that's going to, you're going to understand the extent of the hurricane or tornado or flooding that goes on. So that's in the world of sensors. So when you look at the architecture of what it takes to do a smart sensor platform, again, these are what I call architectural elements that make up the system. So you'd like to power it without batteries if you can. Some cases you can't. Some cases it's, I should say simple, not always so simple, but you can get by with photovoltaic. The technology has moved along. You'll see the technology getting to the point where the photovoltaic cells to do this is very, very small. And there's a great deal of research around motion, thermal, in the area of MEMS, micro sensor elements, MEMS sensor elements. And at the same time, there's been constant drive to take power out of your applications processor. The latest Cortex SAM series, for example, works in microamps. And there's ways of dialing back the power by dialing your clock frequency, your duration, your duty cycle, and so forth. And the newest generation of sensors, MEMS sensors, accelerometers from analog devices is down to 23 microamps working. So it works down very, very, very low. So now all of a sudden here comes energy harvesting, where you can get by with a very efficient, has to be especially efficient boost system, and then charge either supercat the battery, not always battery, how you can get by with ambient energy. But here's the real energy hog. The real energy hog of this architecture is now I have the data I want to transmit. So the data can be sensor data, it can be accelerometer data, and it could be messaging. You know, it could be a human interface with flow speed message. And when you start comparing the average current of each of these stages, and this is typically 100 to 1. Anything else, sum of everything else between the CPU and various sensors, this can jump up in the area of 1 amp, 2 amps in terms of, in the worst case, is 5. Just going back 10 years to transmit the wireless messages or encoded or digital to a cellular network, for example, was you typically used a 2.5 or 3G network. And the specs on those parts, you have to have 1 amp available when you transmit the message. 1 amp, right? So you're basically down to one thing, and that's a battery. And maybe large photovoltaics will work in that scenario, but it's not. My question is how low can I go, right? So where can I go? So the one other thing I wanted to mention about this, so the latest trend in this kind of architecture is to use machine learning or I've seen several papers written where they use the convolutional neural net, but they judge the convolutional neural net by not only its accuracy, classification, but they're judging the neural net on how many millijoules and microjoules in energy it consumes. So I look at a software spec on some of the latest designs in systems, in embedded systems. The stacks, machine learning is rated on energy. So I got the latest thing on energy, on MEMS, on sensing vibration at the very low microamp, 23 microamps. It's not around. But now I have a pattern that's always on, 23 microamps, but on, not off, it's less than microamp. But now I can let this thing run continuously, looking for the next earthquake or atomic bomb. And this baby here can then say, here's the data, but I'm going to go into a supervised learn convolutional neural net that's going to pick up on the pattern. So let's take, for example, I have this on a bridge. So there's a certain waveform I get on windy days, large trucks driving over the bridge, and so forth. So there's a predictable pattern of commonly used forces that you see over a bridge. When you have a certain crack in the infrastructure of the bridge, there's also a unique pattern that's developed. Now, what's tricky is to understand what that pattern looks like that will predict another I-34 event, where a bridge collapses. But one of the hottest things right now in terms of money is the state of New Jersey cannot replace its bridges based on due date. A lot of these bridges are built into the 1800s that are in New Jersey. And if they replaced it just because they're old, I don't know what the bill is. It's over $1 trillion for the state of New Jersey. So it's a lot of money. So you have to have some smarts, right, in the infrastructure to tell you there's warning signs that this bridge may collapse. What's that?
Is there a list
of patterns, you mean?
of bridges?
Yeah. I can give you that list. Excuse me. So yeah, the bridge engineers, the logistics on the bridges in the United States, there's a report every year that comes out. And it's to let people know that you have to at least maintain these bridges. You have to determine. Now today, what they do is they have Rutgers people. They got Rutgers professor actually measuring cracks. So they'll go to a lot of the bridges in New Jersey and look at the crack duration, see if it's changing, right? So I don't know what the frequency is every year. They look at the width of a crack. You have to supervise it and actually manually go in and look at it. So, but they're building libraries, machine libraries of perturbations in the bridge that's indicative of a problem. Okay, so it doesn't have to be transmitting. It's not transmitting data. Forget data. So the classifier is giving it a simple semaphore, simple word of information saying, this is the pattern, it's a T-path that we're seeing right now. This is a pattern we sense. And it may not even transmit it because it may be a big truck that goes over the bridge once a month. I don't know. Yeah.
If you're currently having the information come in, are there any compression algorithms being run before they're trying to transmit data?
Well, in a way, that's what your machine learning is.
Yep.
It's only waking the transmitter up. You don't want to transmit, right? That's
Exactly.
your big power consumer. And the peak is ridiculous. That's what you need supercap just to handle the peak. Even if long term you can integrate the energy. I think I have that. So the power involved is for states. Each one of these states that you're going through on each of these elements, and then you're summing it over the elements, right? And so at different times you want to keep the transceiver off as long as you can, and then you get all this piece data of the transmit is very low, right? If you only turn it on when there's an interesting event that you want something. Anyhow, so I'm going to jump here. So now here's the world of protocols. So I put everything new, on here, and it's kind of an interesting chart because it shows you the range is interesting because if I'm going to put sensors on the bridge, I don't want to have collection points all along the bridge. I mean, that's very expensive. They do that with I-34 now and they'll rebuild the bridge. So you have a chart. Here's your trade-offs, and these are what you call Channing trade-offs. I'll get into that. So here's a direction of higher and higher power. So you see, Wi-Fi is not desirable for the Internet of Things. For what reason? Well, it's powerful. So if I were to put a lot of these systems on, unless I were able to keep it off most of the time, wake it up on what's the phase of sensing moisture in your house. And I want to wake up the Wi-Fi just for that. So here's all the protocol. 5G takes a lot of time. Right? I've designed small 3G systems, 2G systems, and they all contain a lot of power. So in terms of power state, this is much higher. As you go down, you get into low power, which is Bluetooth and Zigbee. And then you get, these are your cellular protocols. Here's 5G, keep dropping the power. LTE-M is low power, reasonably low power. NB-IoT is even lower power. And LoRaWAN is very low, and Sigfox, and there's the energy somewhere up here. So you get under 100 milliwatt once you get into the area of NB-IoT and LoRa. So these are the protocols I focused on. So I focused on what they define as narrowband. So these all sit in below 1 gigahertz. There's a mixture here. These two are cellular, and these two are using unlicensed RF spectrum, what's called ISM, instrumentation, medical, scientific and medical, ISM, which means free. It's free spectrum. They don't pay for it. Now, cellular, you're obviously paying an account for use of cellular. There's good and bad. Now, when I'm talking about LoRa, which we have a senior project going on here, I think it was showing the other we're doing an experiment of trying to bounce LoRa off the moon. So that's one of Dr. Katz's favorite projects in my project. So this is a very low protocol that was rolled out throughout France. So throughout France, you have no problem getting a base station that talks LoRa. Come to this country, this doesn't exist. Unless you're in the city of Philadelphia, you might get covered. Most of the country, you don't have to So it behooves you to set up your own. So you're allowed by law, because it's unlicensed spectrum, help yourself, you know. So typically when we did all the work in the labs here on LoRa, we set it up in our own lab, the gateway. Okay, so we had our own gateways, we had our own portals into the internet. And the transmitters, of course, sat alone. Sigfox is a great idea. Well, like I say, it's limited in France. But here they have a business problem with Sigfox. It's not an open protocol, very closed. And they won't let you build a gateway. And there's no coverage here. So it's kind of like you really want to run a business that way. You can't do it. So they were sold at least a couple of months ago. But anyhow, I couldn't get the product manager of Sigfox. He was here in New York. I said, no. I said, I want to test this. He goes, great. Can you reach, are you within RF shot, meaning a mile or two of Princeton University? I said, no, maybe 5 miles. He goes, oh, well, we're in front. I said, it's his only open gateway is Princeton University. And I said, okay, I'll build one in my lab. I said, we have a lab here. I got a lab. He goes, no, we won't let you do that. We want to take a piece of the action. We want to take the costs. So we have to control the server to bill out your usage. I said, okay, you're talking that. That's not exactly the model it's by my mind. This I can put anywhere. This is very popular in farms where they want to monitor agricultural water levels. They want to measure that. Now there's some new designs I look at that actually will detect certain pesticides in orchards that they're sending them LoRa signals back and you spotted this worm. And pretty cool stuff using convolutional neural net and a low power camera at very slow rates. Okay, so the other axis here is the rate. So you Sigfox, you're talking bytes per minute, which is extremely slow. Turns out to get the range and to get the power, you have to be slow. You got to slow things down. That's Shannon's argument. And so all these are very slow. NB-IoT is interesting because I don't have to buy my own gateway because any 4G and 5G base station supports LTE-M and NB-IoT. So the commercial implementations I've been involved with that's gone over 20,000 units pick and LTE-M because it's reasonably fast and it's got widespread coverage through North America. And it's low cost, low speed. It gives you over twice the distance normal 5G because it's slower, but it's got over twice the distance. NB-IoT has over 4 times the distance and it's even lower power yet. It doesn't do a full handshake with the control channels, cellular. So what it does, it has to re-register itself every time it sees a tower. So you might lose a few seconds. Okay, these are not made for video, so you're gonna have a latency problem with these if you're worried about these. Again, I'm focused, fixed, locked in, the longest distance I can get, and the lowest power.
These are integral to IoT.
Right. The new world of IoT, this is the only way to go. This is slow power. The only way to go.
Well, for computational entities that are distributed, the event takes place and transfer that information versus what's being computed by IoT, otherwise by refrigerator.
Yeah, I just couldn't find a question in that. What was the question on that?
Is there, as an extension to IoT,
Right.
what you're presenting here, and integral to IoT,
Right.
versus what I'm getting in the refrigerator doing computations and interacting with various.
Are we talking about your refrigerator talking to LG remotely? Does your refrigerator communicate to LG? My LG talks to LG corporate when it has problems.
I guess that's the kind of.
That's where it's involved. So if I have to get out of the machine and I need to communicate it wirelessly, if I don't have to go wirelessly, no, that's not part of embedded system. This whole thing is using embedded systems, IoT is part of that. And then I did OT is that you assume you're going to transmit it somewhere. If you're not going to transmit it, you don't have to worry about it.
So your refrigerator is connected to your Wi-Fi network anyway, so there and then as well. Well, you still have to plug it in, that's the thing.
Well,
So it's got full
Right,
power.
right.
I'm worried about what power consumption.
I'm trying to get more to the communicative aspect.
Right. Well, no, that's a good question because my new LG communicates, but it doesn't go wireless. I still have to plug it from my phone. I have to hold it up to my cell
There's a
phone.
different.
It bursts out tones in my cell phone.
Yeah, there's a different mechanism for the
Right.
implementation of manner in which that information is shared around. Communicate.
If it has to leave the area, yeah, that's what you're interested in, and you're interested in the wireless part. And that's a good question because medical, I see all these medical peer-reviewed papers coming out on medical sensors, and you see them. They're right in Bluetooth. I mean, almost every medical sensor you find is Bluetooth when they have to go outside of the box, right? A lot of it's going LoRa because they can get that extra kilometer out of it, so you can go further. Now that might be good for security, but it could, if it's encrypted and you can go the extra few kilometers, you may be able to go right into a medical, a hospital that's within a few kilometers. This might be a good thing. So I'm starting to see the LoRa protocol go everywhere in the new sensor designs.
The word cattle that transfer but which require a lot of the, of course, sterile and stuff like that. Sort of right cattle and track cattle out.
Absolutely. That's a good point. You see it agriculture and ranches, it's all over. I mean, this is what they're doing in ranches. I saw a huge ad on the cover of a Norwegian low power supplier of a chip, Nordic, and they had beautiful reindeer with this thing clipped on their ear, and they're tracking them by the earlobe. Reindeer. There's reindeer. Okay, so this is a little bit about my context here. So I spent a big chunk of my life designing systems that would go from logistics systems, going from wireless assets through satellites, two-way satellites, back to Earth with all digital information, not just location, but load capacity. I had different sensors on, like Walmart's trailer. We had an array of sensors that would be reading inside the trailer. And then we would send it up to the satellite. Of course, location would go with that. So we could develop patterns on logistics, how long it took them to unload at the Walmart stores. So you see a whole pattern, how long it stayed in the yard, how long it took them to drive I-80 from one store to another. So you have a huge map of logistics. So you can predict exactly how long things take and where they are. And Walmart trailers, for example, was one of my customers, and we used to, they would take a trailer.
Well, that's external to what will be implemented within the devices that
Yeah, they transmitted through the satellite instead of cellular, but
back end.
and then all the back end here, yeah. So you take the network gateway and then you go to the network control center. And you have these beautiful maps of, the logistics. Where's my load? And it's beautiful because they had everything. Now, what was interesting about Walmart, one of the first tests I run on this thing is I was testing a cellular system, was when it would go into Mexico. Walmart has seamless into Central America, and they would get hijacked. And actually, it was part of the business model. They predicted So I'm looking at this at the map. I'm sitting here looking at the network data coming back and thrown up on a geo map. I'm like, what the hell are they doing? They're spending all this time right at the Mexican border. Well, it turned out it would be hijacked. And then the Walmart logistics vice president told me that's normal. We understand that. So they take a direct digital feed from our back office, and Walmart themselves can see all where their assets are and how long it's taken, the whole process between loading, unloading at each node. It's a completely visible logics thing. And then we picked satellite because of Mexico and Central America and Guatemala, when they go down for coffee and so forth, and they have containers, we want to track those on board. You're in Guatemala, what is it? Guatemala, excuse me. Sorry. But the satellite we used, we had perfect visibility into that, all the way into South America. What's that?
That's private.
Right, it's a private network. So we had got to deal with WorkCom on the satellite. Anyhow, so that's a little bit where I started from. And then this just gives you a shot of all the sensors you have. You have an amazing array of sensors. I presented the idea to Walmart VP that we can put radiation sensors in, we can put nuclear sensors in, we could put biological sensors, we could put chemical sensors, we could put air sensors in, and go, you're going south of Mexico. I mean, this might be a useful thing at the border, And anyhow, I got a lot of interest, but they were the people that wrote the checks was logistics model, They said, well, we have Homeland Security that does this. You have to talk to Homeland Security. And anyhow, I thought that. So this was the size of the photovoltaic we use, and we powered it through photovoltaics, which is pretty cool because it takes upwards of 5 watts for the transmitter on the satellite to transmit, and it had to be sitting in a long time in standby while I was looking for a orbital satellite to come by.
How large in reality is it this large or?
Well, this is the nose of the trailer. I guess that's not good. These panels about a foot and a half. Not too bad, but they powered the whole thing. This white box underneath was the antenna. They track the. Well, here's the specs on that photo. It's 9 ounces. It's 8 inches by 3.4 by 47 inches. And it lasted 10 years. And by the way, the way they commercially rate PV panels is hailstone, 1-inch hailstone when they're outside. 1-inch hailstone at 50 miles an hour. I don't know where it became from. And they talked about delivering 1.25 watts. And of course, that went into a storage medium. And there's all kinds of interesting stuff about this. I don't have enough time, but I wanted you to look at this. Let's see if this is working. Okay. So on a lark, a couple of us, I was sitting in research at the time, and the guy that ran the lab said, hey, we got all this data. Let's see if we can plot it. Now, we happened to plot it at the same time Katrina was going on. At the end, it was cleanup after Katrina. We were like, we got all this Katrina data because our trailers were at the, GE trailers and Walmart trailers were sitting at the Superdome in Katrina. And then I had these tracking devices sitting on General Electric generators. So you can see the generators is colored in red. You can see them backed up. This is time sequence. And you can see them back up at the damaged bridge. See them starting to back up. And this is Louisiana, Superdome in southern Louisiana. And the green is all flooded in that area. Okay, so there's no way. So here's the idea. Here's the insight. The insight is this is like a watch. This is going off like a fine-tuned clock or watch. And nobody can use the phone. No one in that whole area has a phone access. They don't have power, and they don't have cellular. Cellular towers were smashed during Katrina. And same thing happened during Maria. So in the meantime, all our stuff is like transmitting like a normal day through the satellite and back. So we said, well, why not, instead of just logistics, why don't we just put a port on it for short messages, so then we could have the driver use it for typing critical, mission critical, life death type messaging, and still get out and use the satellite that's built into the trailer. So the whole satellite transceiver is on the trailer, monitoring logistics. And the power grid is just how much electricity is going to generate. Anyhow, so that was where this whole idea came from, is like, gee, if I can get the power and the cost down low enough, I could communicate. So fast forward from Katrina to Maria. What do you think happened in Maria? You know, it touched down one of the islands out as a Cat 5, and it completely tore up the infrastructure, the cell infrastructure, the power infrastructure was immediately out. And it took almost a year in the mountains area of Puerto Rico for them to get power. And in the meantime, the first time they got a telephone connection was this was a project called Project Moon by Google, Alphabet Company X, where they carried in the payload a base station. So they turned on the base station, but what they turned off was voice. So they just said you can send messages to anybody you want, you know, and they could scale 21 base station. They can support 20,000 people.
That was
Not voice, but messaging.
That balloon was stationary then.
Right. No, it floated in place, slow movement, very slow movement. Yeah. It wasn't like the Chinese were controlling it.
No, but it stayed there over time.
Right.
In a particular place.
Right. Right. So, but immediately, but here's what they did. They got permission from the FCC and T-Mobile, I think T-Mobile and AT&T, to overlap on their spectrum. So they were able to bring up a base station, and your phone all of a sudden comes alive, even though you're using Verizon. Use it because now you have the spectrum programs in for all the carriers, and you got to get the permission because this is precious space, but people were out of it. Now this took place. This is the second thing that took place in communication. The first thing they did was this that got communication. Okay, that's something else they did. The other thing is AT&T set up a drone over Puerto Rico where they can come in, and that's holding a base station. Payload is another cellular base station. But here's what's cool is the Harris does these ad hoc networks, and they use ham band frequencies. So they got a group that are senior HF engineers, and this is used for satellite backup. So when there's no more satellite, these guys, Harris has the solution. So they have all the equipment, and they have the people staffed, and they had some support staff flown to Puerto Rico, and immediately they had communication with their military HF backup equipment. So they were getting the first few days, the first week. This is the only communication in Puerto Rico, and was this kind of stuff, military grade HF Harris equipment. So when everything hits the fan, they bring out the military equipment, which is this Falcon series of RF 5800, and these are HF. So I looked up the spec and I got all kinds of information. I started reading the spec and how they with HF, you have to understand the propagation is always changing. So it gets tricky, you know, how to deliver a product, deliver communication. And so all of a sudden something kicked in my brain and said, well, you know, my favorite radio club when I was growing up was in the early 60s, and it was in Trenton, and it was called Civil Defense Club. So what did we used to sit around? I was a kid, so I'm sitting around talking with guys that were, I don't know, 4 or 5 times my age. And they turned the club, this was in 1964, into a backup communication that we could take this equipment. Collins was making the best HF equipment at the time, and I learned how to patch HF communication into the telephone circuits. So I could bring up a telephone call anywhere in New Jersey on a switch that I can manually override and bring in signals from here, voice signals from here. So I was learning how to do that at these meetings, these workshops. It's pretty cool. Now, what happened just before 1964, the Cuban Missile Crisis? The president himself put his family underground because he was convinced we were going to be hit with a nuclear. So our little group, and I'm just a kid, I'm learning how to do backup for a nuclear bomb. And it wasn't good getting under the table, get under your chair, get under the table. This was get the diesel generator running, this huge multi-kilowatt generator we had in the building, still there, by the way, a nuclear fallout shelter in Hamilton. And get the system communicating and working after an EMP or a nuclear bomb. But anyhow, this brought back a lot of old memories, and I thought, well, and then fast forward, they needed backup when the Pope came to Philadelphia. So I got enlisted to come and work. They call this the Armageddon pod. So during a complete failure, this is self-contained. There's a solar panel or a board that plugs into this that powers it. And this is all UHF equipment, and then it also has HF for global communication. So needless to say, I was looking at this wondering what they were expecting when the papal visit came in. You know, this was supposed to be for, quote, hospital backup communication. So the hospital didn't have power. And anyhow, just a quick refresher. So you can go great distances, fantastic distances, if you slow down the traffic, where your channel capacity in bits per second becomes very low, and design it and limit the bandwidth, narrow bandwidth, and the further you can go with narrow bandwidth and the least amount of power. So that's the usual the overall direction. This is a little bit of how much you can energy harvest. This is a energy harvested NB-IoT development board. Okay. You need super efficient DC to DC converters. And let me zip through some of these things here. Okay, and then the other thing you have to carefully is you got to design the propagation path and losses. So if you're an engineer on a communication system, each one of these nodes has a gain or loss in decibels. So you basically calculate your. Okay, this is what it looks like. So this is an example of a LoRa communication to a satellite. You start with your transmitted power at 20. That shows the path, 100 minus 147.3 dBm loss that you end up getting over the propagation to the satellite, and then basically you have a loss from a gain from the antenna to the dBi gain. I stands for isotropic over vertical. And then you cable you lost the dB and so forth. So everything is then dependent on what's your receive sensitivity in dBm minus dBm, will tell you whether the system's going to work or not. All right, so this brings me fast forward to we have a local guy that happens to some of you people may know the Joe Taylor, Dr. Joe Taylor. Yeah. So Dr. Joe Taylor detected pulsars, and he is obviously an expert on attenuation of ionosphere up, well beyond the ionosphere. Anyhow, he's retired from Princeton. He has a Nobel Prize when he discovered pulsars through measuring. And for fun now, this is his amateur radio hobby. He designs protocols to address fading paths, Doppler, which is where the frequency shifts paths, and then how to boost the receive sensitivity to extreme levels. So he's like a wild man that does for passion. He's retired from Princeton. He owned he was the head of the physics department and astronomy department of physics. But now what he does for fun is he sends up new protocols, wireless protocols for us to test on amateur radio. So he's gifted us with a whole bunch of protocols, and one of his early ones it was called WSPR Whisper, which was a propagation reporter. So he used to use this as a beacon to detect on what frequencies had a propagation path to wherever he wanted to go or wherever he'd go in the world. So fast forward here, let's see here. Okay, so so he's got all these protocols that go down very low. Now the Whisper protocol works at 10 hertz. So he's taken Shannon and has knocked it down to 10 hertz.
That's in conjunction with some basic hardware as well.
Right. But no, he's using a PC. So he's doing all the software defined radio and bandpass filtering on the radio, in software. So he's using a standard PC or a Linux system. He's running all this stuff. So you can experiment with it. I'm working with the balloon people. For their project this year, they changed the protocol to Whisper. So they're working with Whisper, right. That's a wireless propagation recorder. Okay, so now everybody's into this now, and they're saying, hey, this would be a great idea. So somebody came up, first it was Tektronix offered a product that would allow remote Spectrum servers to be set up. So for a mere $40,000, you can buy one. So the hobbyist community took over and said, hey, we need something to see our Whisper signals, or JT8, JT9. These are all, JT stands for Joe Taylor. So this is his experimental, this is what he does for fun, protocols. And so somebody said, hey, I can do that with a dongle, $25 TV receiver, USB receiver. I can do it with that. And then I could present through the DSP software on a fast PC. Now I need a multiple core PC. I need to run pretty fast, but you can do it. It's free, and it's all free code. So all these dots are people in the world that have assembled. You can buy it outright. You don't have to build anything. Kiwi has a complete transceiver that takes your Spectrum where it's sitting, plugged into your antenna in your backyard or whatever, or no one's very short antenna, long antenna, and then it sends it on the internet. So anybody can use your server, his server, and look at the whole spectrum and pick the signals off of the spectrum. So that opens a lot of possibilities, good and bad, mostly good, I think, but negative. So all these dots represent somebody that has set up a Spectrum server that you can look at the signals, and you can select whatever protocol you want, and it'll look like this. Okay, so this is actual screen I captured. So late one night, I had selected, let's see here, Whisper. I had selected the Whisper protocol to demodulate this signal. I pointed to this signal, this frequency. And sometimes there's little cue cards up here which tells you where the protocols are at or what frequency. Now this particular server is sitting in Carrefour, France. Does anyone know where that is? I don't know where it is, but I happened to look it up on a map, and it's right at the Syrian border. So so here's what's being decoded. Just dropping out the Whisper code. So it's talking about the receive level, and this is signal to noise level. There should be the transmitted power. This is 8.3 watts, and then the message, and then there's a short message here. These are short messages. So if you let that roll, all of a sudden you come into they're tracking all these military vehicles in Syria and in they look like Russian vehicle. So they're using this as a tracking tag in the Soviet area in Syria for tracking assets. Now it might be, I don't know, 100 kilometers away. But now I'm on this local server that's going into Syria, and I'm seeing it from a server in France. Is this insane or what, right? So this is the kind of thing that has just been banned in China. You can't do this in China. Anyhow, so here's my point. So, okay, so I like these very low energy protocol. So now everything that gets sent, you can send it. If you receive this, you can automatically forward it from your code into a map or a database, common database. So, but just by taking a glance at that, I can tell you what the propagation conditions are at what frequency, at what bands, which is pretty amazing. I mean, you can at a quick glance, you can see what works and what doesn't work. So if I'm going to send messages into Syria, I can see the propagation path from North America. Okay, now here's another adventurous soul. This just went live last month. So this box, it's about less than 4 by 5 inches. This black box. There's a transceiver.
It's like a QDX.
QDX. Yeah, already we've got one here, man. Do you build one yet?
Yeah, it's the first batch.
Yeah.
That's all that- that was on the board.
How do you like it?
First, let's say,
It's
first
the first
version was exercise until the latest version that I have. We solved a lot of issues.
Yeah.
They said I wanted to forward to it.
You gotta wind your own torrents, yeah.
Wind the toroids and supply better quality wire that we're not down a lot of shorts.
Wow. So here's a smart amateur radio hand buff in version. Let's see. But so he says, wait a minute, I could get this distance with Whisper. I know how they're doing it. How are they doing it? Narrow bandwidth, 10 hertz or less. They're using a certain number of tone modulation, which he's doing. And it's very slow. He slows everything down. These are messages, right? They're not video, they're not audio, so he can go slow. And he says, hey, wait a minute, I got a cell phone. I'll use it as a terminal, and I'll write an application that will take the HF messages coming in. It'll actually look at the spectrum, and then you can communicate through your cell phone, but you're not using your cell phone SIM. You're just using the cell phone. This becomes your wireless transport, is your QDX amateur radio transceiver, the tiny one, it's this big. And he put one in his car, get this. He throws this in his car, you can see in the back seat, throws it over the back seat. He puts up a vertical antenna on his trunk, and then he drives for, I don't know, 400 or 500 miles a day he has to drive. It tracks it all the way there. He gets text messages all the way, 450 miles. It's pretty cool, right? Now he charges $10 for that application. John doesn't want to spend the $10. Anyhow, I just thought that was cool. It's called, it's a pager. It's really a text application called HF Pager. And it's in the Android store. So that's something I wanted to try too. And there's a number of applications now that take advantage of the JT protocols for conversation, emergency, Vario. I don't have that screen, but that's one of the popular ones. So what we're doing at the Ham Club, we have an emergency situation where we can communicate with different protocols like this, with JT.
So the benefit of this one, you have JSA call.
JFA call, right.
It allows you to send a message.
Right.
The other ones are just a signal for back
Right.
and forth.
Have you used this before?
Yeah.
Would you like it?
Yeah.
Okay, so all this ultra low power, long distance, we're talking hundreds of kilometers. You can possibly go with this stuff if you get your propagation right, which with Whisper, you can get your propagation. Whisper supports 10 telemetry channels. But I don't know if you knew that, but it supports 10 telemetry. So somebody could piggyback messages on the Whisper protocol also. Anyhow, so we're back to, okay, this is some of the tests I did with the narrowband cellular communication to show that I was getting a plus 17 dB advantage in sensitivity. This is something I did in my home lab and basement. I actually went into concrete. So we've been doing tests in concrete with this. Anyhow, 5G supports these protocols not the Joe Taylor ones, but I mean, they support NB-IoT and LTE. Again, it's the same kind of direction. And the way they've divided 5G, people think 5G is just high-speed video, right? Well, that's just one of 3 use cases that they're trying to cover. So they have ultra low latency. If you're going to do machine control, you're going to run a factory, or you need to do remote surgery, control surgery remotely. That's how they split up 5G. So there's a lot more to 5G than just the. Now, notice how it's interesting. The ITU specifies 5G, and there's IEEE is involved with specifications on 5 and 6G. And what they specify on this narrow bandwidth sub-gigahertz communication is the length of life of the battery. So what's the goal in the use case? 10-year battery. So you want something that'll last 10 years and work at very low energy, which is perfect, right, for disaster emergency communication. Okay, let's see what else I got here. There's some of a little bit of the math on a Shannon's ideal. Notice it's tied to bandwidth,
What were the licenses that we had?
ISM, and that in this country, people use 930, 915, 930, 433, right?
Some people commercial to call it, some people, it sounds good. Same thing that.
How many time?
It's actually.
Not a time. Okay. All right, I'm going to wrap this up. Any questions? It's pretty cool stuff, you know. So I'm advocating for get your license, and we can do more experiments if you're interested in this technology. I think we're in for a rough road in this country. I think we're, you know, the famous how many seconds to midnight clock. Everybody know what that is. It's changed, and you got 2 superpowers, atomic superpowers. Now this stuff would work if it was vacuum tube, but you have to put this in shielding if you're going to use it. So QDX is cheap enough. You can buy them assembled if you want to pay another $45. If you don't want to build something, Hawaiian toroids, and put it in a shielded container, and you can weather that.
I think with the latest version of QDX is it also includes 11 meters, which is a license CD. And it also covers 6 meters, which is amateur radio, but it will 49 megahertz license. So I know in Taiwan, they've been adopting these JSA fall
That's cool.
over a license spectrum to avoid detection. So
Yeah.
it's definitely something interesting. 35 questions, get a technical license, super easy.
Yeah, get it. We have.
Friends can do it in a day.
Yeah, so we have a lot of clubs around here that will issue a test, and there are students here today that are taking a test. We have a ham cram, and you can get your license today. You want to take the test, not that hard. What's that? Well, I'm involved, David Sarnoff Radio Club and DVRA, which is the one by the airport. They meet by the airport. So there's 2 active ham clubs right in this area. David Sarnoff Radio Club, DSRC, and DVRA. And we have been meeting, David Sarnoff has been meeting at the Red Cross in Princeton. We're going to have it here this Tuesday if you're interested. You're coming this Tuesday, right? Did the IEEE note come out? Go out? Okay, I'll check with Sam. All right, any other questions?
It's a complex topic. I think you did a good job.
Thank you.
Keeping the story.
Yeah. Well, I'm always in the background. I'm always thinking we could do this, that we could really set up a sensor network to look at the border situation. And I actually presented this to a presidential, his staff, presidential. Yeah, I presented it, and they said you missed one thing. Not this presentation, but I presented one where talks about the radiation sensors and NBC sensors. I wanted to put on the GE trailer sensor system, telematics system, and they said you forgot one thing. Once you sense a biological or radiation problem, what are you gonna do about it? It's too late. Yeah. Well, then, you got to have feet on the ground, you know. I'm like, I admit it.
Well, not all scenario.
Huh?
Like
Not-
cigarettes.
Kiss your ass goodbye, right? But we know there's problems coming at the border right now, some serious problems, and I happen to think you know, we're at beginning stages of a Cold War with China. The fentanyl coming over the border, it's a wide open border. Forget the government telling you it's closed. It's not closed. You know, be careful where you get your news sources, right?
So we're talking about yesterday.
Yeah, they lying through their teeth, unbelievable. But
Is there any thought, given to, security,
Mhm. yeah, what people are doing, first of all, in the terms of the ham license, you cannot have encrypted information. In emergency, I don't think anybody's going to arrest you. On the other hand, most of the successful encryption work is end to end, and the two ends basically. And even out of that, it's been I have a whole IEEE deck on the history of encryption, and it's not been pretty.
Yeah, that's why you have to one, so what I mostly want to do is negotiate your key beforehand, so just you and the
Right.
other person have it, so that when you're actually communicating, what you're actually communicating is encrypted data.
Yeah.
And it's decrypted on
Well,
your end.
that's what we're talking about, specialized, silicon.
Right. So, and we've seen the banking community settle on DES. That doesn't work. So we go double, triple DES, and 128 AES used to be good enough, not good enough, and now it's 250. So one by one, I mean, like I said, I have a whole deck starting with Enigma and World War II, and the Germans were convinced and they can prove their encoding machine was secure. However, there's something called cribs, like people would put on their messages, Heil Hitler, or they'd talk about, well, I jumped back into the past. So this is the German encryption.
Germans.
Yeah, Germans had encryption. Well, we were encrypting too, yeah, and the English. So the English, Churchill we had a taste of decrypted Nazi messages through the Polish. The Polish mathematicians had, a couple of them had broken the code. But then the Germans figured out they should make their encryption a little bit better, tighter. So they added another rotor. So they started progressively made it more and more difficult. So Bletchley Park, you know, there were people, pretty good people that worked there, including Alan Turing, who designed the first computer. He wasn't the first one to get it working, though. That was, he went to a guy named Gordon Welchman. Anyhow, I got a whole pitch on that thing. But the point is that anything you say is encrypted and secure is not. So, and I don't believe in blockchain being fully encrypted either. Well, the Chinese banned it because they couldn't break it, but then they have their own version. Now, what do you think? How encrypted do you think that one is?
Right. Yeah, that's the math is sound. It's just people fail. Going back to mentioning about key phrase.
Yeah.
Key management, key distribution. Got to your point about Bletchley Park. Every June there's this Polish Day where they recognize the Polish help for breaking Enigma.
Yeah.
I mean, I highly recommend it here that they do England in June.
That's
Spend
great.
time going to Bletchley Park.
Yeah, I'd love to see that. Yeah, that's great. Yeah. I usually follow the news clip, like they had, you know, they had employed thousands and thousands of women too as Y operators, and some of the work they do I've documented. It's pretty amazing stuff. You know, the high-speed Morse code, you had to be able to copy it at 25 words a minute or faster, and they had trained. There were a lot of women that were doing all the direction finding, so they knew where Fritz was working in Northern Africa. I mean, it's just mind-blowing stuff. They would go up and down the bands looking for people. If they changed the frequency, they'd recognize them by the fist or their code patterns, the way they, crazy stuff. I mean, amazing. And then Gordon Welchman, turns out he was the guy that worked with Alan Turing, because Alan Turing couldn't get his computer working, literally, his cracking computer, you know, his code cracking computer. So Gordon Welchman figured out how to do it and how to do it twice as fast. So he had it set up in parallel. So he invented parallelism. He left. Everybody else, you know, they burned everything they had in Bletchley Park, so the enemy would never get it. They have a veil of secrecy, 25 years, and if they caught you saying one word, you go to jail, and they were serious. They stripped the Gordon Welchman left right away, came to Massachusetts, moved from England to Massachusetts, and was immediately hired for MIT to build the first computer, design the first computer. So his first job here was with MIT, And then the government picked him up, MITRE, which is one of the spook operations that the whole thing became NSA, right? So he designed the first security wireless system for the NSA. Was Gordon Welchman. Then they found out he just wrote a book on Bletchley Park, and they stripped everything away. They took his clearances. They put him out of they kicked him out of MITRE, and they just said you can't work in any place around here because he says, what are you talking about? Other people have published books. They said, no, you're not. You can't do it. That's how serious they were on the secrecy. But to this day, there's the Cubans use the 5 alpha word encrypted packets because they use the one-time pads. That's the one thing that's proven in this whole encryption mess is the one-time pads have been secure. So you listen today, there's certain frequencies where you can hear the 5, the numbers. No, they're number stations. They're not numbers, and they're still there. So what spies are they sending it to? I don't know. But anyhow, all right, guys, lots of fun, real interesting subject.